Everyone, this is lecture number 22, E211 Analog Circuit Design. Myself, Dr. Hitesh Shrimali from IIT Mandi. So last time we were talking about a new chapter called feedback. Mainly we were talking about there are two different aspects. It might be positive or it might be negative. But we are interested in the negative feedback. And we also learn one thing, that if there is a system in negative feedback, the closed loop transfer function might be 1 plus a0 divided by 1 plus a0k, where loop gain is equal to a0k and it has to be much higher than 1, so that the transfer function only depends on the feedback factor. And that is what we are doing in like op-amp based circuit. If you remember, we never take care of the op-amp's gain and all. However, in reality, that creates sometimes problem, and a0 is not to be always infinity. It has to be some number, and which has to be replaced to find out the closed loop transfer function. By the way, this is closed loop transfer function, right? There is one small mistake last time when I was doing this. So I was looking at this like in hurry. I gave input and output impedances. However, the correct one is this one, where voltage amplifier is the one where input impedance is like those impedances are given uh, as according to this one. However, we'll discuss this in detail maybe after maybe one or two lectures, or maybe the next lecture might be on different kinds of amplifiers. So let's start with the theory. The next important part is how to find out the loop gain. Loop gain is nothing but multiplication of the feed forward system gain A1 and the feedback network gain K. So the multiplication of these two is going to be equal to A1K. However, if you are keen to find out the value of A1K, because loop gain has to be much higher than 1, so in that case there are various techniques. So one of the famous technique which is used everywhere, even if you go to any industry, you have to do this with the feedback, and you have to find out the complete loop gain. So in that case, this is the thing: sense and feedback is equal to break. So if you want to find out sense and feedback, so these two things are there: sense mechanism and the feedback. You need to you can break an input with test signal and measure the output in open loop. So you need to break the loop. This is the important part. After breaking the loop, you need to apply some input at the input of this loop, and you need to measure it. So if you measure it at the output, it will be the multiplication of these two things. While doing this, of course, input x goes to 0, right? So then and then you can do this. So before to start, let's look at some of the possible example of how to break that. So now you can break the loop. So from this loop, I am breaking my loop over here. Let's assume that I'm breaking the loop as broke over here, and I'm calling them N and M. And I'm applying here some known potential V test and measuring the output over here. Look at this one is output and this one is input with the V test. While doing this, Vx goes to 0, or all other inputs are 0, all other inputs, so that when I'm measuring from here to here, the output like Vn is going to be equal to A1 times K times V test, right? So we know that Vn divided by V test is equal to A1K, and that nothing but a loop gain. And by looking at the dynamics of A1K and all these things, you can find out the loop gain is much higher than 1 or not, and you can predict on stability and many other things on that. But that has to be taken into account at the initial stage itself. So apply an input at the input port. So look at this: apply an input at the input port only, and sense an output at the output node only. So you need to make sure that you're doing it at input and output port. So if you are doing this by breaking the loop, if you are you are making something like this, that V test is here and you are checking the output over here, Vn, then it's not allowed because this is the output port where you are connecting the input, so it's illegal. Do not do this thing. Maybe we can discuss few more breaking of loop. If I am not breaking the loop there, but I am breaking the loop just after the right after feedback, right? And of course input is 0 and the loop has been broken over here. So this is of course output port and this is input port, so I am connecting VTest and Vn, and if I am measuring this now in open loop, I am going to see that A1 times K, that's the A1 times K times VTest is equal to Vn. So of course I'm again repeating the sentence that apply an input at the input port only and sense an output at the output port only. This is very very important. So as I told you with the red color box, that this is illegal thing because we are applying output port with input signal and input port with some output, so that's not possible. It's an illegal. Do not do such kind of feedback to find out A1K and such other mistakes. You can do it accordingly, right? So now let's get back to the real business where there are salient features of negative feedback. One of them is gain desensitization, or it's a PVT independent. This is already proven. We have looked at with op-amp in feedback with some resistors, capacitors, or anything. Like, it does not depend on the open loop gain of an amplifier, as like when the gain is a open loop gain of an op-amp is infinity. If it is not infinity, then the whole thing will not work, and like you need to keep those things into your calculation, and that will affect the accuracy, or that will affect input offset voltage and many other parts. But we have seen that how it's affecting the input offset voltage, that how much value of the minimum input offset voltage can be detected. It is decided by the open loop gain of the op amp. Other than that, there is one more thing. It's going to extend your bandwidth. What I mean to say is, if the A1, which is the feed forward system, is equal to A0 divided by 1 plus S divided by omega 0 with the feedback network gain K, if I am looking at the closed loop transfer function y by x is going to be equal to A0 divided by 1 plus S by omega 0 and 1 plus K by omega A0 divided by 1 plus S by omega 0, right? When you simplify this, you're going to have A0 divided by 1 plus KA0 divided by 1 plus S by 1 plus KA0 times omega 0. So here you can see that the small signal uh, gain at low frequency, or the DC gain, is A0 divided by 1 plus KA0, or you can say that it has been divided by 1 plus KA0. And if you look at the bandwidth, it has been increased. 3 dB bandwidth has been increased by 1 plus KA0. By the way, 1 plus KA0 is nothing but a loop gain. In the case KA0 is much higher than 1. So this is actually approximated to KA0, and that is a loop gain. So you can call even 1 plus KA0 as also loop gain. So you can say that the overall gain is actually divided by a loop gain, and closed loop bandwidth is extended by a loop gain. So this is also loop gain. This is also loop gain, right? So you can say that 3 dB bandwidth increases by the loop gain factor, and loop gain is much higher than 1, then closed loop gain is only depends on the feedback factor. Still, that is the case. Look, we are not saying that it's not, but it depends on what value of precision you want. Accordingly, your output will be there. Anyway, so if it is a single pole with uh, single pole with pole at omega 0, and small signal AC gain is equal to A0 divided by 1 plus S by omega 0, then you can find out the UGBW of the open loop system. By the way, UGBW is nothing but right now the 3 dB pole is equal to omega 0 and the gain is equal to A0. If I draw the magnitude plot with respect to frequency, this is omega 0, and value where it's going to cut this, it's going to be equal to A0 times omega 0. That's the gain bandwidth, right? So the UGBW in this case, or GBW, is equal to A0 times omega 0. That was asked over here. Now going one level further, if it is closed loop, what is the UGBW? Interestingly, UGBW is nothing but the small signal AC gain or the low frequency gain times the bandwidth, which is 3 dB, as this is single pole system. So still UGBW remains same, it does not change. In the closed loop, the UGBW does not change, 3 dB bandwidth is changing and gain is changing. So overall gain bandwidth means output divided by input when they are becoming 1 is not changing. The value is same, A0 times omega 0 if it's a single pole system. So you can see here, if the system is like open loop system has A0 and omega 0, that's the magnitude plot with respect to frequency. But when it's in, like this one is open loop, but when you are keeping that one in closed loop, the gain is depending only on the feedback factor, right? Or you can say that that's going to be equal to A0 divided by 1 plus KA0, and the bandwidth is going to be extended by a loop gain. Whatever the omega 0 was here, it's going to be multiplied with the loop gain. So if this is extended, that thing is also extended. So this side it's getting down and that side it's getting extended. But when you are looking at the UGBW plot, it's following the remaining dynamics as it was in the open loop, and UGBW remains same. So that does not change. So now, as I told you, the salient features of the negative feedback systems are gain desensitization, which we know how it's extending the bandwidth. However, UGBW remains same. And on top of that, it will change the IO impedances as well. So let's see how it's changing the IO impedances. As we know that if it is voltage controlled voltage source, we want Rin to be infinity and R out to be as low as 0, right? This is what we want. So but these numbers are actually will have some finite values. It cannot be infinity, it cannot be 0, it will be in kilo ohm, mega ohm, or here might be 50 ohm or something. So if it is kept in negative feedback, what is going to happen, whether it's destroy this characteristic or not, or it will improve it? Let's see that. So let's assume that we have a, a circuit which is a common gate amplifier. Here you can see that it's a common gate amplifier connected in a feedback with two resistances R1, R2. So it's exactly like this one. If you look at this, it's exactly like this. Where inside this triangle there is a common gate amplifier, right? Notably, the way it has been connected, it's a negative feedback, right? Because this is negative terminal, this is positive terminal, right? Relatively, notably, this is also a negative terminal, right? Because negative to negative will be that the gain is actually positive over here. Okay, so and from gate to source the gain is negative, so this might be considered as positive terminal and this will be considered as negative terminal. We already discussed this in previous lecture, previous some of the lecture, that how these are plus and minus. But from gate to source to drain, it's a positive, like if this is negative, this has to be negative, by the way, right? And vice versa. Okay, so if I'm drawing the equivalent block diagram of the same thing, then this triangle is nothing but a common gate amplifier. This is going to be taken care by the inherent property of a transistor, because this is connected at gate terminal and this is connected at source terminal. So it's relatively plus and minus, and this is one more feedback factor where it's equal to, if I'm looking at Vx by V out, it's equal to R2 divided by R1 plus R2, right? It's already known to us, and we are going to call it K. So that's answering the question number 2. But if we are interested in A0, which is nothing but open loop gain, so in that case open loop gain is going to be equal to the open loop gain of the common gate amplifier. The common gate amplifier gain is nothing but GM1 plus GMBS1 times RD. I'm not considering channel length modulation, and it might be like eta times, sorry, GM1 times 1 plus eta times RD, where eta is equal to GM1 divided by GMBS1. So, sorry, GMBS1 divided by GM1, that's the eta. So in that case, we can find out the closed loop transfer function. So the closed loop transfer function is equal to right, as it is known to us already, because it's A0 divided by closed loop gain is nothing but A0 divided by 1 plus A0K in negative feedback. Notably, this is negative feedback, right, because of these terminal value. Okay. Now, next question is, which is more important over here, find the input and the output resistances in an open loop and in a closed loop feedback. So let's start with this. Already, like, we know what is the input and output resistances in open loop. For if you are interested in open loop, you can find out this value. The output resistance is from here, and that's equal to, output resistance is nothing but RD in shunt with RO1, right? If you are looking from input side, input side is nothing but 1 by GM1. That's Rin. Now let's look at the thing what is happening in the feedback. So if feedback is given to us and channel length modulation has not been considered, then I know that the current which is flowing through this one, which is ID, is equal to GM times VGS, which is already known to us, where VGS is nothing but VG minus VS, VG minus VS, where VG is nothing but R2 divided by R1 plus R2 times the voltage over here, right? So this VG depending on this potential, and that potential is nothing but Ix times RD, because that's the current when we are interested in finding out the input impedance. Notably, like I forgot to tell, so this is same as what we are doing in the Thevenin equivalent theorem, that we are applying some known potential Vx, and now we are, and at that time all other things are connected to ground. So in that case, we are interested in Vx by Ix. That is going to give me the input resistance. So in that case, ID is known to me, which is Gm times VGS, and that is going to give me the value Gm times Ix RD. This is the potential available at this point. Right? So Ix is the known current. Same current is going to be flowing through this part and this part, both. And we have to make sure that R1 and R2 value are so much big that the current will not flow from here, right? It's very big number. R1 and R2 are very big, so that no current is flowing from this branch. And of course, at the input side, there is no current because the input impedance is infinite. This side is also infinite, so no current is flowing here or here, right? Because it's a relatively very large number. However, RD and other things are smaller, so things will be passing from here. So compared to RD, like RD has to be lower, much lower than R1 and R2, or you can say that compared to RD, R1 and R2 has to be very large value, so that no current is flowing from R1 and R2. So in that case, we can write down these equations, and the node potential over here is Ix times RD times gate potential, that is R2 divided by R1 plus R2 minus Vx. Vx is this one. So this is Vg, this is Vs, and this is the node potential. Sorry, this entire thing is Vg. The multiplication of these two is Vg, where this is node potential times the resistance, right? Okay, so other thing is ID is equal to minus Ix. So if this is ID and Ix are in equal and opposite direction, so it has to be minus. If you replace that in that equation, what are you going to see? You're going to see that Vx by Ix is equal to 1 by Gm times 1 plus R2 by R1 plus R2 times Gm RD. Okay, so if this is the case, so in that case, in this case, we can see that from here to here, from this input to this side, the gain is actually common source amplifier, and common source amplifier has gain of Gm times RD. We are not considering the channel length modulation. Okay, so this is the gain. Feedback factor is from that point itself. The feedback factor is R2 by R1 plus R2, which is acting as K. 1 by Gm was input impedance, if you remember, it's 1 by Gm. So that was the input resistance, and it's getting multiplied by 1 plus Ka0. So as this is a voltage controlled device, we wanted to have the input impedance to be infinity. In this case, it's earlier it was 1 by gm, so it's getting improved by a loop gain, because this quantity is loop gain, so it's getting improved, right? Or you can say that the take home conclusion is, if you are keeping the system in a feedback, the input resistance is getting multiplied with loop gain, so it's getting more and more value and going towards infinity. So if this k0 is much larger value, it's a 20, 100 or maybe 1000, as it is higher, it's going to give improvement to Rn. And similar thing we are expecting for the output resistance, because output resistance is already known to us, that what is that value, Rd in shunt with R01. If okay, Rd only, because there is no channel length modulation, so it's Rd. So let's see what is happening. And in the case of closed loop transfer closed loop resistance, so in that case, at the output I'm connecting the known potential Vx. I'm interested in finding out Vx by Ix. While doing this, input is going to 0, VDD is also like, it's also 0, right? While doing this, we know that the current is not flowing here, by the way, because this R1 and R2 are much larger value. R1 and R2 are very high compared to other resistances, so current will flow only in this direction or in this direction, right? So addition of these two is equal to Ix, and Ix is nothing but this side, it's gm VGS current is flowing, where source is 0 and gate is connected to R2 by R1 plus R2 times Vx, right? So this is VGS, so gm times VGS in this direction, and looking at up that direction, if this potential is Vx, the current is Vx by Rd. And after doing this, rearranging the equation, you are going to see Vx by Ix is equal to Rd divided by 1 plus R1 R2 by R1 plus R2 times gm Rd, right? Where gm Rd is nothing but your open loop gain of this common source amplifier. Rd is the resistance in open loop system, sorry, output resistance in open loop when it's an open loop. R2 by R1 plus R2 is nothing but a feedback factor. So I can write down this thing in a simple way, that closed loop resistance equal to R out in open loop divided by 1 plus Ka0. So in the case of input resistance, it was getting multiplied by 1 plus Ka0 to support the fact that I need more and more resistance. Similarly, I need smaller and smaller output resistance. In that case, it's getting divided by 1 plus Ka0. So you have to make as large as K0 or the loop gain, so that your 3 dB bandwidth is extended properly. Your gain becomes desensitized by like closed loop gain desensitized, and you are having more and more accuracy. You can have input and output resistance improved way in terms of the in terms of the the input the loop gain. So if you know that what kind of configuration you are using, voltage current, or like VCVS or VCCS or CCVS or CCCS, accordingly the resistances will be multiplied or divided by a loop gain, where loop gain is nothing but 1 plus K0, and you can write down the answers directly. So this is already, I should write down that improved both rather than calling it, because this particular sentence is valid only for voltage control voltage source or the voltage amplifier. Now one more thing is linearity. Linearity is depending on one fact, that generally we want y equal to mx plus c, right, for the linear equation where c equal to 0. But in reality you are not going to have that one, but you are going to have such kind of things. You will have all the harmonics. If first one is divided by a loop gain, second one is actually divided by loop gain square, and third one is by 3 times, and you can say that overall each harmonic is divided by 1 plus ka0 times raised to n, where n equal to the number of harmonic. In the case of fundamental, it's 1, second, 2, third, 3, and if you're looking at all these harmonics are also getting improved, and you can see that as these numbers are actually raised to n, you are getting a significant amount of noise reduction, or you can say that the noise floor will be improved compared to the fundamental. So this is again a very important factor in our case, that you will see some improvement in linearity wise. So in closed loop, not only the gain desensitization, bandwidth is also extended. However, UGVW remains same. IO impedances are getting improved, rather than calling this, because it's getting improved. You have to see the what kind of amplifier it is, and the linearity wise, you are seeing it's also improved, or the harmonics are getting decreased. Now, like this is the illustration I'm keeping for you, that find the open loop and closed loop gain. So you can find out when you are adding, like this is an amplifier. I want this one. After adding these two resistances, so this is V in. So after keeping that, what is happening, that's what you need to see, right? So open loop and closed loop gain with and without the load, which is RD by 2. It's exactly, I have taken RD by 2 just to have the maximum power transfer theorem to act over here. So just I kept some value. So you need to add that one, and you need to find out the open loop and closed loop gain. So it will be very little change from the previous examples where RD by 2 was not there. So now the output resistance changes by RD by 2 in shunt. Notably, the current will flow from RD by 2. Note that, because in R1 and R2 were kept at very high value, where RD by 2 is actually lower than this RD. So current will flow from here, here, and here. Now all three are comparable. So do the analysis accordingly. The current cannot flow from R1 and R2 as they are much higher value. But if it is in this case, the current will flow from here, and you have to consider RD by 2 also in finding out open loop closed loop gain, and of course for other things also, input and output resistance. For the same thing, let's say if you have such kind of network where you can see that this is minus and this is plus, so if I increase this, notably this is plus terminal, this will has to decrease. If this is decrease, this will decrease. If this is decrease, as this is common source, it's also going in positive. So then it becomes positive feedback. So this has to be minus terminal. This might be the minus terminal. Then this is going down. If this is going down, this has to be going down, and this has to be going. Okay, I made a mistake or what? Okay, if this is plus terminal, this is going up, this is going up, this is also going up, this is going up means this is going down. Yeah, so this entire loop is negative feedback. When it's come back, you have to make sure that negative feedback will be in the reverse direction of this one, so that it becomes the negative feedback. So right now it's negative feedback, right? So there are a list of questions for you people, like you can do it at your home. So list the advantages of negative feedback system. So that is known to us. There are many advantages. One of them is gain desensitization, bandwidth, 3 dB bandwidth, and UGW. You can write about that. Other than that, it's linearity, and you will see the IO impedances is getting improved. Right? List the type of multivibrator. So there are astable multivibrator, bistable, and monoshot, or the monostable multivibrator. You can explain the difference between each of them. I believe you understand that. Most important theory behind this is it might be like those are the oscillators we are, and the output is always progressing one. Here you can calculate the open loop gain A1. Right now it's only A1. Look at this. But in terms of feedback gain, it's combination of these two. So you have to find out Vy by, let's call this one as Vx. So Vy by Vx, you need to find out. Maybe for that intermediately you can find out Vy by Vx1, because the input is over here is nothing but R2 divided by R1 plus R2 times Vy. That's the input over here. The input is R2 divided by R1 plus R2 times Vy, and Vx divided by Vy is nothing but, so by the way, this has to be for feedback factor, Vx divided by Vy is equal to this multiplied by, so you can remove this multiplied by, it's a common source gain, so minus Gm times Rd, in the absence of channel length modulation. But in the presence of channel modulation, it will be in shunt with Ro. Right? So this is the feedback factor. You can find out now closed loop gain by keeping A1 divided by 1 plus Ka1, where K is this one and A1 is some value which is not known to us right now. You can find out the input impedance, you can find out the output impedance for figure 1 and 2. Right? So this is what I am giving to you. Maybe similar questions, or the questions are available in Behzad Razavi also. Right? Okay, so let's move further to different types of amplifiers. So you might have 4 possibilities of output and input, and we have 2 quantities, voltage and current. We are not dealing in the any other derived quantity, but we are talking about the fundamental 2 quantities, which are voltage and current. So if that is the case, you might have 4 kinds of amplifier. One is known as voltage amplifier, one is known as current amplifier. There are 2 new kind of amplifier which are known as transimpedance and transconductance amplifier. Okay, so transimpedance is Z, this is V, and this is Gm, and this is I. Right? So the notation wise, impedance is by Z, transconductance is Gm, and current is I, and voltage is V. If it is voltage amplifier, we know that the input quantity is voltage, output quantity is voltage, and because of understanding of loading effect and all, we know that input impedance has to be infinite and the output impedance has to be 0 to accommodate the next level of the circuit. When we are going to cascade it, we need this one, high input impedance and low output impedance. It's already known to us, right? So voltage amplifier will have these characteristic, or it's like a VCVS. If you look at the other configuration, which is current amplifier, where input is current, output is current, then we want low input impedance and high output impedance. It's exactly reverse of the voltage amplifier. This is triple CS. Other one is transimpedance amplifier. If you need to have the impedance, so if in this box I am keeping impedance, actually this is a transfer function. If you understand this, this is the transfer function. Like in this case, if it's a voltage amplifier, I wanted output as voltage, input as voltage, and the unit of this one A0 is equal to unit of A0 is voltage by voltage, right? In this case, output is current, input is current, means the unit of A1 is nothing but ampere by ampere. And if looking at this one, output is like this is impedance, then output has to be voltage and input has to be current, just to make sure that it's V out divided by IE, makes it quantity impedance, or you can say that in ohms, right? So the input is current and output is voltage. In that case, we know that the input if this is current, so similar to current amplifier, input resistance has to be 0, and output is voltage, so it's similar to voltage amplifier, and the output resistance has to be 0, so both side impedances has to be low. This is what we want, right? On top of that, you might have the next category, which is transconductance amplifier, whose unit is mho or Siemens. So in that case, the output is current, input is voltage, and that's how it becomes I out divided by V in because this quantity is a transfer function. So transfer function is going to give you GM as transfer function, where input is voltage, output is current. Using voltage amplifier characteristic, input impedance has to be very high or infinity. Using the current amplifier characteristic, output has to be infinity. So in both the cases, input and output impedance has to be high. So this is what you can keep it in your analysis, or you can say that it's voltage control current source. In this case, it's current controlled voltage source, right? Now let's understand few more things. If I want to model it, the first voltage amplifier whose input resistance I want it as infinite and output resistance as 0. If I want that, I'm making a model where the input impedance is infinity. So you can see plus and minus, but it's infinity. That's why it's an open circuit. But at the output side, V out is nothing but, I can write down what I'm expecting as V out. It's A0 times V in. And I want this as a voltage controlled voltage source. So from input voltage, I want this as acting as a voltage source. So it's equal to A0 times V in voltage. If I am having a multimeter and if I measure it, I'm supposed to see A0 times V in. However, there is one more characteristic, that R out has to be 0. So the source resistance offered by this one R out is 0. So there is no resistance I'm keeping over here. So in the ideal model part, the voltage amplifier should have following model, where input is open and output side is short with one voltage source whose value is A0 times V in. Looking at current, where input resistance has to be 0, while making the model, this is I in, where the input is shorted and output has to be infinite in shunt with a current of A0 times A1 times I in, because this is current control current source. So output has to be a current value, right? And this is coming from these two things. Notably, here there is one more branch which is having the infinite impedance in parallel. Look at this, for the current, the impedance is in parallel, which is infinite. Now looking at transimpedance amplifier, where what I want as transimpedance amplifier has output quantity is voltage and input quantity is current. So at the output, I want V out as some Z times I in, where Z is actually the transimpedance. So what I want is, at the output I should have some voltage source whose value is RO times, RO is coming from here, times I in. By the way, if you are making this as just a resistance, not having any other value, then it's also known as trans resistance amplifier, because it's only talking about the resistance. However, in reality, there are some capacitance and inductance are also there, or maybe you can say that there are some frequency component. In that case, this R0 is not going to be just a resistive part, it will be impedance. So it can be replaced with the whole impedance driving point function and multiplied by I in. I in is the input current. Notably, like for this case, I could have done this one with some R out, but R out value is 0 for voltage source, so it's shorted. And in this case, input resistance is 0, so it's actually directly going towards ground because it's 0. Now, transconductance amplifier or GM amplifier is the one which is a voltage controlled current source. So output should have the current whose value is GM times V in, with following things, that input impedance is infinite and output is also infinite. So this has to be modeled like this. So all these models were ideal one. Look at this. These were ideals only. But in realistic, let's think about various examples where intentionally I kept some of the things as non-realizable or the wrong model, because that is more important whether you can model it or not. But for that we need to understand what kind of amplifier it is. Let's start with A, B, C, D, E, F, in accordingly what kind of amplifier those are. So first one is voltage amplifier. I'm going to write just V or VI, GM, or the impedance. This is voltage, right? This one is also voltage. This one is voltage and input is current. Look at this. So V out by I in is making impedance. This one V out by I in making impedance. This one, look at this quantity, it's current, output is current, look at this, and the input is voltage, so it's transconductance. And this one is again like output is you can look at this, output is I out and input is I in, so the output current is A1 times I in, so this is current amplifier, right? I believe there is no doubt in this one, right? So in that case, whether it's realizable or not, let's start from the first one, where it's a voltage amplifier or the voltage controlled voltage source whose input impedance we are expecting as infinity and output impedance as 0. By the way, this is we want in actually in ideal case. So there is, you can see infinite impedance is already there, but I'm keeping something in shunt with that one, then this quantity will become reduced or it will become realistic. What I mean to say, Rin, if it is not ideal one, which is infinity, if I want to change infinite to some real number where I'm supposed to keep the resistance either in parallel or in series. So right now you can compare, one of the model has to be wrong because A and B both are voltage controlled voltage source, both are having similar characteristic, input impedance is infinite, output impedance is 0 in ideal case. But here the input resistance has been kept one time it's kept in series and one time it's kept in parallel. So if you are looking here and looking here, Rin in shunt with infinity, Rin is waning. In this one, Rin plus infinity is going to be same as previous one. It's not making any sense by keeping any resistance in series, right? But if you are keeping input resistance in parallel, then it makes sense. So if you are if you have the voltage controlled voltage source, you need to keep the resistance in parallel at the looking at the input side, whereas at the output side, where we wanted that output is 0, so there are two possibilities. One, I can keep it in shunt, one I can keep it in parallel. So which one is more realistic? Because I want to make the value other than 0. So here it becomes R out in shunt with 0, it's again 0, right? R out in shunt with the 0 resistance coming from this voltage control voltage source. But in this case, it becomes R out plus 0. So it's R out. So this model is more realistic than this one. Similarly, like there are two impedance amplifier whose characteristics are known to us. You can apply same theory and you can find out whether we need to keep it in series or in parallel, right? Because in this case, keeping in parallel does not make any change, it's 0 only. And similarly, like here, the input is R in rather than 0. So which one is more realistic here? It looks like this one, but this one is not. Similarly, you can look at the R out, and similarly you can find out for E and F. The answer wise, you can see like B and D are not realistic. You can think about it, and if you find any difficulty, you can like write me in comment box, or you can mail me, right, so that I can help you. Okay, so now our next target is we need to find out what kind of amplifier it is. Right now, let's understand one more thing, that why we are doing all these things. We found out that what kind of amplifiers are there. Either it's A0 or K, where A0 is feed forward system gain and K is the feedback gain. So in any of the transfer function, it might have any kind of amplifier, either voltage, current, transconductance or transimpedance amplifier. In any of the case, you are going to connect A1 with K and with the summing amplifier. So you need to make sure that you are connecting current with current, voltage with voltage, so that there is no problem in loading, or it will not create a problem. You cannot connect voltage terminal with directly to current or current to voltage and vice versa. For that, it's very important to know that where, like which kind of amplifier it is and where to connect that one. Or sometimes it has to be converted from voltage to current or current to voltage, just to make sure that you are connecting right quantity when you are keeping in the negative feedback loop. So this is very important, and while keeping in negative feedback, make sure that it's negative feedback only, because sometimes it happens that it's positive feedback. So if it is positive, it's like no matter what you are doing, but output will go either to 0 or VDD, and you are end up with unstable system or the oscillatory system. So for that, it has to be understood that which kind of amplifier it is. Already we did such kind of things. By the way, here you can see that input is here, so you can find out the input impedance for input port, and the output impedance at the output port. So this is output port. We need to find out what input impedance is there. So if I'm looking inside this, I'm going to see the gate of the transistor and it's infinity, right? And looking at the output, I'm seeing that there are two branches, one going up, one going down. So across a current mirror or the current circuit, it's infinity. The source of looking at source of M2, it's 1 by GM, name it as 1 by GM2. By the way, we agree that 1 by GM2 is in some value of ohms, like 100 or 200 ohms. We are going to call it as low, and something is more than 1 kilo, which is going to be high. So input impedance is infinity, output impedance is low. Then what you can say, that this particular amplifier is a voltage amplifier, or it is a voltage controlled voltage source whose input impedance is infinity, and output impedance is low. However, it's not low, but the value is 1 by gm2. We assume that it's low, right? Now identify the voltage like type of the amplifier in this case. So I'm it's already very easy to find out because here it's already written. But if it is not written, if I'm connecting here, so looking at the input port, the input impedance, the output port, the output impedance. So looking from here, it's a source of a transistor, so it's 1 by gm1. Looking at output side, there are two branches across current source or current sink, it's infinity, and upside it's a source of transistor, so it's 1 by gm2. So input impedance is 1 by gm1 and output impedance is 1 by gm2. So this is also low and this is also low. If both are low, then input quantity is current and the output quantity is voltage. So in that case, the amplifier is transimpedance amplifier, and whose input and output impedance both are low or zero, right? So this is already known to us. Let's try a few more. So I need to find out what kind of amplifier the MOSFET is. So looking at gate side, the input impedance is infinity. Looking at drain side, the output impedance is RO1. RO1 is in the range of kilo ohms, so we call anything in kilo ohm or more than kilo ohm, we call it infinity. So input impedance is infinity, output impedance is again infinity, so output is current, input is voltage. So in that case, this particular thing is known as voltage control current source, or you can say that it's a transconductance amplifier, right? Sometimes they call it operational transconductance amplifier. Instead of calling it op amp, we call it OTA, operational. This is just for your information, operational transconductance amplifier, rather than calling op amp. Op amp is actually voltage amplifier. Okay, so in this case, again it's already written, but yeah. Input port is this one and output port is this one. Looking this side, it's 1 by gm1. Looking at output, it's actually RO1. So RO1 in kilo ohm, and we call it high resistance. 1 by gm1 is in ohms, we call it low impedance or low resistance. So output is current, input is also current, and such amplifier is a current amplifier, or we can also call it current control current source amplifier. And it's a it's an amplifier whose input impedance and output impedance is, okay, sorry, I cannot write that. Input impedance is low and output impedance is high. Maybe another theory of how to connect these amplifiers: voltage control voltage source, or current control current source, or and so on, like all four categories of amplifier, how to connect A1 with K in feedback. That will be the next topic of understanding. We'll talk about this maybe in the next lecture. So thank you very much for today.